I'd like to show you a few things that I've been kind of involved in for the 3 or 4 months, last 3 or 4 months. And, okay. As you probably guessed, I've been dealing a little bit with some electronic devices, and so I'm going to try and introduce you to those a little bit, and so we'll just have to see how it goes. I've been working with integrated circuits and schematic symbol for operational amplifier. An integrated circuit is like this, and it's got a minus input and a plus input and an output here. So basically, it's called a differential amplifier. It amplifies the difference of 2 signals or 2 voltages here. Now they have what's called a very high gain. In other words, it's like turned up a lot. So you generally use a feedback component, which is a resistor, and feedback into the negative input. That's called negative feedback. So what happens, what you're trying to do is if you have, say, a small voltage here, it amplifies it maybe 200,000 times, and it inverts it. Since it's the minus, it comes out minus whatever the voltage amplified by 200,000 times. So you feed back a portion of that into the input, and that essentially cancels, and so it turns down the volume to a reasonable, usable level. And generally you also have a resistor on the input, and for most purposes ground the plus. So what you're doing is you're taking a signal in reference to ground and amplifying it here, controlling the gain or volume rather, whichever you prefer, for this resistor. And so this is the basic building block, and with these there are quite a few configurations, and you'll see a few of them this evening. But this is the basic building block. It's, the integrated circuits are about like so, and they contain very small. They contain, actually, the integrated circuit itself is about a 1/16 of an inch square, and then it's put into a larger package so that you can handle it. And you can make quite a few things out of it, and that's what I'd like to go on to explain. Okay, now what I've done here is used a second type. Well, first of all, this is a differential amplifier, as I explained before. You can, instead of grounding one signal, you can go in to both signals. You can take the difference of the 2 signals. In other words, if you've got a plus signal and a minus signal, and so if you put a voltage across them, if the voltage between grounds, now the ground's no longer on here, you put your ground here, and when the signal goes positive this way, you get a positive output. When it goes positive here, you get a negative output. What's interesting about this configuration is when you have the same signal on both of them, the 2 signals, you've got a plus and a minus, and they cancel, so you get no output. So this makes it possible to have a very high gain amp. In other words, very, very quite a bit of volume out of it. And in terms of the difference of these 2 signals, however, you can have a relatively large voltage superimposed on both of them, called the common mode signal, which you don't see at the output. So I'll try and go very quickly here. Basically, what I've got here is a device that can amplify voltages over your muscles, that appear over your muscles. When you flex a muscle, it appears on the surface of your skin. And one problem with this first type of amplifier, which I've kind of destroyed here now, is that it amplifies anything that's on the electrode. Now, unfortunately, you're probably all aware when you unplug a plug from a hi-fi or something, you get a buzz. And what that is it's 60 cycle from the AC lines that are all over, you know, I mean, it's all over. You can't get away from this stuff. And so it'll completely mask the signal that you're trying to measure on your skin. So you use what's this differential amplifier configuration, and your whole body is picking up like an antenna, the 60 cycle frequency. And what you're doing with this differential is everything that's over your entire body is ignored. You're summing the difference of these two. The difference when they both have the same signal is 0. However, the difference from one place on your skin to another place on your skin is then amplified quite a bit, and then you can go on to use that in other ways, which I'll get to in just a moment. Now basically, you'll come through a capacitor. I have some drawings downstairs that will be a little more complete than this, but these capacitors will block DC voltages, which we're not really interested in here. DC is direct current. I don't know what backgrounds you all have, so perhaps I should explain. AC is generally alternating current, and if you plot, this would be time here, and this would be voltage. In other words, a positive voltage like the plus end of the battery, negative voltage. Okay, DC, you just pick a level and it stays relatively constant over a period of time. Alternating current, or AC, goes positive and then it goes negative and then it goes positive. Now this is a sine wave here, which is also a sine function mathematically. And you can get various types of waves. This is the simplest wave, but it does illustrate alternating current. Now capacitors will pass alternating current, however they block direct current, except when the direct current is turned right on, you'll get a little heat, a little like a pop. But like I said, though, we're interested in the alternating current, so we put a couple of capacitors. Then this particular differential amplifier, normally these don't have an extremely high common mode rejection ratio. In other words, they do, nothing's perfect, they do amplify some of the common mode signal that's present at both of them. So what I've used here is two of the same basic amplifier configuration. However, this time you've taken the negative feedback and put it directly back into the input. So this gives you a gain of 1. So all this does basically is give you a buffer between the signal you're trying to pick up, so that also it gives you a much higher input resistance. In other words, it doesn't short circuit the voltages on your skin by doing this. Then you go into the more traditional differential amplifier. In other words, this amplifier amplifies and isolates the voltage off of this electrode, this one off of this electrode. So you're essentially keeping this differential amplifier configuration, going into a second differential amplifier where you have feedback. And this, again, is your negative feedback and controls your gain. This is a variable resistor. You slide volume control, basically. And okay, so now on the output of here, then you've got the difference of these two signals and ground. So you have basically 3 electrodes. You ground yourself, and that gives every voltage has to be in relationship to something else. In other words, a voltage is a difference between 2 electrical potentials. So what you're doing is you're putting yourself at 0 potential and then measuring the difference in 2 other places. The difference whether it goes higher or lower than your body potential. So, okay, so now I put 2, the frequencies we're interested in are between approximately, say, 100 hertz, which is cycles per second, and about 1,000 hertz, which is a fairly low frequency. It's in the audio frequency, and you'll be able to hear it in a moment. But so what I've added here are 2 other. I'll just draw a block diagram here because it's a little easier for a high cut and a low cut filter. So in other words, we're not interested in any voltages below, say, 100 cycles. So anything that alternates slower than this cycle is from positive peaks. In other words, it's one complete cycle from where it starts to where it has to get to the same voltage. You can take that starting at the 0 point, and that's 1 cycle, or at any point along here, but in other words, you measure how many of them per second. So it vibrates 100 times a second. And we're not interested in anything that's closer to DC or slower alternating than 100. And also, we've got a cutoff at about 1,000 to 2,000 cycles on the upper limit. We're not interested in that. So basically what we've done here is we've blocked DC. We're amplifying the difference between two electrodes and using a differential amplifier, and then we're using a high and low cut filter. And then I've got a voltage divider, which simply gives you a fairly standard output voltage. And we'll stop right here for now, and I'll go ahead and show you what this does. I'm just going to clean my skin a little bit with some alcohol, and it gets some of the grease off and gives you a little better contact. I'm just going to use this muscle as sort of out in the open, so you get to it pretty well. Then you use what's called a transmission gel. It increases the conductivity of your skin. And so basically you want a good electrical contact. Your skin isn't a very good conductor normally. So, especially for these low voltages, it's down in the hundredths of a volt that we're measuring, which is why it's so difficult to, that's why the differential amplifier is necessary, is because when you're measuring that low voltage, it can get lost very easily with the electrical noise. And these are just little copper discs that I've inflated, and they'll work as the conductor. And this is just connected into the differential amplifier here. I've got two leads that lead into the differential amplifier and the ground. And you can ground yourself around the wrist, which is a good, just sort of, there isn't too much activity going on there. So I'll go ahead and put this wire over here so it'll stay put. Also, this is an oscilloscope, and basically what you're seeing here is actually this signal is sweeping by fairly rapidly. It's probably very difficult to see in the back, but basically that gives you time, and then up and down will be voltage. So essentially it draws an instantaneous graph of what you're seeing here. And it's connected in, I'm going to speed up the sweep here because we're interested in a little bit higher frequency. see that you get more of a 60 cycle hum. You pick this stuff up, it's all over, like it's something that you're not usually aware of, but if you step off it, it's people in the front row can see this is the 60 cycle, which is the AC coming from the lights and whatnot, and it picks up considerably when you step off onto the wooden floor, because the wooden floor is acting as a conductor for these electrical fields and whatnot. Okay, so basically, then, I'm not sure, I suppose you can hear that in the back. So you're basically hearing, when I tense my muscle, you get an electrical signal. And that's what you're hearing amplified. Now this is like used medically and whatnot, but I'm not really like into it from that area. And so there's some other interesting things that you can do with this voltage. Basically, you've got an AC voltage that's been amplified enough to be useful. It isn't useful on your skin, really. You have to amplify it to the point. Then you can use these circuits again to do various. You can do a transformation. You can take any kind of a voltage and make it into any kind of another voltage. And basically, since it's proportional to the harder you tense your muscle, okay, the harder you tense your muscle, the louder it gets. So that gives you some kind of a starting point. So now there's an interesting device where you can input a voltage into it. Okay, a DC voltage, and out of it you get a square wave, which looks like a square. It says periodic. In other words, it goes from plus DC to minus DC to plus DC in a periodic fashion. It's an alternating wave. You can get a triangle wave out of it, which is a triangle. This is another integrated circuit. It's about so long, about so wide, and it has 50-some transistors in it, which is what's nice about this stuff, because you couldn't, a few years ago, the average person, I'm not really an electronics person, the average person couldn't have done this kind of thing. However, now it's possible, because you're working with these block diagrams, and you also get a sine wave out of it. So basically, if you can get this kind of a voltage, convert it to a DC voltage, this proportional again, feed it into this thing, you can get voltage, by the way, controls the frequency of the output. The amplitude or volume stays approximately the same no matter what frequency it is. Okay, so you can come out here and come down to say A and go into what's called a diode or a rectifier. And basically what this does is it allows current to flow, say from negative to positive. You can go, there's two different ways of considering current, but you can consider it as flowing from negative to positive. And so it'll allow current flow this way. However, we'll block the flow going the other way. So in other words, what you're doing is, say, at the positive terminal, then you're seeing these positive peaks coming off of here. And then when it tries to go negative, this device blocks the flow of currents. So essentially, where you see peaks up here, you can take the center line, the DC line, which is 0 volts, and you can take anything over it, gets let through, okay, and then when it gets down to 0, you just get it just ignores it, then you'll get a positive peak again, and then 0, and then, so in other words, what we've done here is we've rectified, and we have to come down here a little bit, we've rectified, rectified, I guess is about the best phrase for it, the AC voltage to make it into DC. Now there's still a problem with this. It could be fed directly into here, but that would mean that the frequency would sweep and then go back to the set frequency, and in other words, the frequency increases when you give it a voltage. So what this would do is every time you see a wave over here, which is going pretty quickly, so you get a real quick fluttering of the frequency. So to prevent that, you can put it into a capacitor. Now, a capacitor is just two plates, basically two metal plates that are very close together, and they're made in various configurations. It's usually aluminum foil wound up into a coil so that it takes less space. But basically an electrolytic capacitor can store a charge. In other words, as electrons flow through this circuit positive, it forms a positive charge on the positive plate of this. In other words, you've got positive voltage in relationship to ground. So then as the voltage falls off, this positive charge is still present, so essentially it'll lower the DC level. So what I've done after that then is put it through a variable resistor into the op-amp again. This is, as I say, this op-amp configuration, the original op-amp configuration, by the way, is used for the high and low cutoff filter. And what you're doing is you're allowing some frequencies to feed back and not others, so that you get a higher gain in the frequency range that you're interested in. That's how these filters operate. So anyway, we're going into another one. This one just is a straight feedback, so that this is just an amplifier. So in other words, again, you're amplifying this voltage. You get a very small voltage here, and I'll show you this voltage now. Okay. Now we'll have to turn up the sensitivity a little bit. And okay, so you can see it. The voltage that you get in the front row, at any rate, you can see that it stays about at 0 volts DC. Then when you flex your muscle, you get positive voltage. Okay. Now, as I mentioned, you want to smooth it out a little bit, so you can turn up the resistor going into the input of the amplifier. The amplifier will drain the charge off of the capacitor, so you can vary this resistor to vary the amount of time it takes to drain off. So as you can see, it takes maybe 3/4 of a second to get back down. Now, if we increase that resistance, it takes even longer. You can see it just kind of drifts down. And so when you flip it to the output here, you can get kind of a siren effect. In other words, what I'm doing is I'm putting voltage into this capacitor, and then when I relax, the voltage is drained off through this resistor. So you basically got what's, sounds kind of like a siren. Okay. So what we're seeing here now, by the way, is the square wave output coming out of here. And so what happens, I'll show you again, we'll flip back to that DC, and we have to turn the sensitivity up a bit on the oscilloscope. But what we're doing is increasing the voltage here as I strain, and then it slides back down, allowing the oscillator to go back down to the base frequency. In other words, it stays at a low frequency. When I squeeze the muscle, the voltage goes up here, and then as it drops back down, it slides back down. So, okay. Now, the front couple of rows can probably see this. This is actually a square wave, and it looks square. It means that it's going from 0 to plus DC to 0 to minus DC in a square. This integrated circuit is called a function generator. It generates these waves. However, it's more than an oscillator. They used to have just oscillators that basically was a sine wave or possibly a square wave. Now they're called function generators because they're actually generating a variety of mathematical functions. They can be described mathematically. And we've got the triangle wave, which isn't quite as loud here. The reason the square wave carries so much better is it's made up of actually a variety of sine waves of different frequencies. And so basically you've got, if you break it down into components, and I'm not that great on the math end of it, so I can't explain it so well, but at any rate, these sharp corners indicate, whenever you have a sharp corner like this in a waveform, it indicates there are high frequency components. And so if you put a square wave in front of this, since you've got your high cut filter, it's going to round off the leading edges of these square waves, because that's where the high frequency components are. So it begins to look more like a sine wave, because you've reduced the high frequency component. But at any rate, so these high frequencies carry quite a bit better than lower frequencies, and also this amplifier is about 20 28 years old or so. And it also doesn't amplify the lower frequencies quite as well as the higher frequencies. Okay, so let's see where we're moving. Okay, now there are a number of other things you can do by varying the time constant. You can get it down. This is what this is doing. We'll flip it back to the DC, and what you're seeing here is basically this is with no time constant, and the capacitor is discharging almost as quickly as it charges, and so every one of these pulses over here charges up, and then it takes a little bit of time, so you get sort of like this. This is the time constant here as it discharges. So you get a peak like this, and so now as I gradually increase it, you can get kind of like the when you turn it real long, you can get a siren effect. But when you kind of turn it to a medium here, you're not seeing too much on the amplifier, hearing too much with this signal because it's basically DC and amplifiers for the most part. Well, these differential amplifiers and integrated circuit amplifiers will amplify from DC. However, the lower cutoff generally on this amplifier and most amplifiers is anywhere between 20 and 50 hertz. So you're not hearing that DC. In other words, you don't want to put DC into your speaker because it just pushes the cone out and holds it there. And it isn't too good for speakers, so that's why you're not hearing anything. You hear a little bit when you turn the time constant way down because every time it changes, a change is basically AC and will be fed through a capacitor. A constant level is not fed through a capacitor, and so you're not, the input to the amplifier is protected with a capacitor. Okay, so we'll turn this up to kind of a medium here.
give you kind of these little
bulk or muscle at a certain sort of average tension level to hit a note. And I've been carrying things around all day, so it's going to have a tendency to waver a little bit. Plus you've got this kind of waver effect because you've got to hit kind of a compromise. And so what I'm trying to do here is adjust the time constant so that it smooths it out enough to hear a note, but not so much as that it takes too long. So let me see what I can do again. Also, this is the time constant. In other words, this determines the discharge rate through the amplifier, and then this determines the output. So you can sort of scale for a given muscle tension. You can increase the amount of voltage on the output for a given input voltage. So I've got both of these that you're kind of balancing back and forth. If you turn the gain up here, a smaller